Hi, in this video, I'm going to guide you step by step on how to use the I4I General Metal Loss Screening Tool for API 579 Part 4. The link to the tool is in the video description, and this video is meant to be used together with the tool. API 579. Part 4 exists because general metal loss from corrosion or erosion is one of the most common integrity problems we deal with in refineries, and it is also one of the easiest problems to underestimate. The dangerous habit is assuming a few thickness readings tell the full story. Part 4 gives you a disciplined way to screen whether your case can be handled using Part 4 methods or whether you have conditions that require a more rigorous fitness for service route, such as Level 3 methods or even a different part if the damage is not truly general metal loss. Before we start, I want to explain a few key terms in a simple way. Corrosion allowance, sometimes called erosion allowance, is the thickness you expected and permitted the component to lose over time based on design and integrity planning. Future corrosion allowance is the additional thickness you expect to lose before the next scheduled inspection based on corrosion rate trending and service knowledge. Minimum required thickness, often called T-min, is the thickness you must have to safely carry the design loads based on the code and design basis. Minimum measured thickness is the thinnest reading you have in the affected region. Average measured thickness is the average thickness in the affected region. Those last two matter because Part 4 is built around general metal loss behavior, where thickness averaging makes sense, but it can become misleading if the damage is actually localized. Now here is how to use the I4I screening tool. You will answer every question from 1 through 29 by selecting yes, no, or NA. Use NA only when the question truly does not apply to your equipment or your situation. For example, if a question is clearly about external pressure and your case has only internal pressure with no vacuum scenario, NA is appropriate. But do not use NA just because you are unsure. If you are unsure, treat that as a sign you need to gather information, improve your inspection coverage, or confirm your design basis before you can confidently screen the equipment. After you answer all questions, click the button that says Check if FFS is needed. The tool will give you a result. When it indicates FFS is needed, it does not mean you failed. It means the screening found credible conditions where you need a defendable engineering basis rather than guessing. One important thing about this Part 4 tool is that question 2 is a gate. It is intentionally placed early because it prevents unnecessary work. If metal loss is still within the specified allowance and you still have enough thickness for the planned future allowance until the next inspection, then a Part 4 assessment is not required for that specific condition. You document the data, trend it, and continue monitoring. Now let's go question by question with detailed refinery scenarios so the logic becomes very clear. Question 1 asks if the identified condition is strictly metal loss from corrosion or erosion and not another flaw type that must be evaluated under another part. A realistic refinery scenario is when UT mapping shows thinning near a weld, but phased array UT also flags a linear indication at the weld toe that could be a crack-like feature. In that case, you cannot treat the whole situation as just thinning. The crack-like portion must be handled under the crack-like flaw route. If the condition really is only corrosion or erosion thinning with no crack-like indications driving the concern, select yes. Question 2 asks whether the metal loss exceeds or is predicted to exceed before the next scheduled inspection the specified corrosion or erosion allowance, or whether there is not enough thickness available for the future corrosion allowance. A realistic refinery scenario is an FCC slurry line elbow where erosion is aggressive. Today, you may still be within the allowance, but the corrosion rate trend shows you will consume the remaining allowance long before the next inspection interval. That is a yes, because the case needs assessment. Another scenario is a crude overhead circuit where your latest inspection shows thinning, but it is still inside the allowance and the projected loss until the next inspection is still covered by the remaining allowance. That is a no, and in that situation you record the measurements, update the corrosion rate, and continue monitoring without running a full Part 4 evaluation. Question 3 asks if the case is appropriate to evaluate under Part 4 as general metal loss, recognizing that Part 4 may be used for uniform or even local wall loss treated as general metal loss, and that if thickness profiles show clearly localized behavior, Part 5 may be used as an evaluation option. A realistic refinery scenario is a vacuum column shell course with broad thinning over a large band of the shell. That fits Part 4 very well. Another scenario is a localized patch under a pipe support or near a small area of wet insulation. If you scan it and it behaves like a discrete local thin area, Part 4 can become overly conservative, and Part 5 may be the better evaluation path once you confirm it is localized. If Part 4 is appropriate for your case as a general thinning problem, select yes. Question 4 asks if the metal loss is confirmed to be on the correct surface or surfaces for your records, with the affected region clearly defined. A realistic refinery scenario is corrosion under insulation on a pipe rack line. You must confirm this is external metal loss, define the start and end of the affected band, and make sure you are not mixing it with internal corrosion assumptions. Another scenario is internal corrosion in a sour water stripper overhead line where the damage is clearly on the inside diameter. If you have confirmed which surface is affected and you can clearly define the region, select yes. Question 5 asks if the component is not operating in the creep range. A realistic refinery scenario is high temperature piping at a heater outlet in a reformer or hydrocracker. If the service temperature is high enough that creep could be a controlling damage mechanism, then this screening approach is not appropriate for Level 1 and Level 2 metal loss assessment. If your equipment is in typical refinery temperature ranges where creep is not a concern, select yes. Question 6 asks if the original design criteria was in accordance with a recognized code or standard, meaning the design basis is traceable. A realistic refinery scenario is a pressure vessel built to ASME Section 8 with nameplate, drawings, and design conditions available. That supports defensible minimum required thickness. Another scenario is an old piece of equipment where the design code is unknown, drawings are missing, and the basis for allowable stress is unclear. If the design basis is not traceable to a recognized standard, select no because you cannot defend minimum thickness without a credible basis. Question 7 asks if the metal loss region has relatively smooth contours, meaning it does not behave like a notch and does not create significant local stress concentration for Level 1 and Level 2 applicability. A realistic refinery scenario is broad corrosion that gradually transitions over inches, like general thinning on a column shell. That is smooth. A contrasting scenario is a narrow erosion groove downstream of an orifice plate or control valve where the metal loss forms a sharp transition that behaves like a stress riser. If your metal loss is smooth and gradual, select yes. If it is sharp and groove-like, select no. The question 8 asks if the component is not in cyclic service or if it satisfies the cyclic service screening procedure referenced to Part 14. A realistic refinery scenario is a compressor discharge circuit that sees frequent trips, startups, and pressure swings, or a reactor feed line that sees repeated heat up and cool down cycles. If cycling is frequent and severe, it can create fatigue concerns that are outside what simple screening assumes. If the service is steady with infrequent cycling, select yes. If the service is strongly cyclic and you have not screened it appropriately, select no. The question 9 asks if you identified the Part 4 component type using the component classification approach, such as straight shell or straight run, nozzle region, or discontinuity and junction behavior. A realistic refinery scenario is a straight section of piping in a crude unit which behaves differently than a nozzle-to-shell junction on a drum, and both behave differently than a transition cone or head-to-shell region. If you have correctly identified what type of component you are evaluating so you apply the right rules and limitations, select yes. Question 10 asks if the component is within the Part 4 applicability limitations for component type and loads, including internal pressure and, where applicable, external pressure and supplemental loads for the selected assessment level. A realistic refinery scenario is a vessel shell course carrying internal pressure and normal sustained loads. That is typically within scope. A contrasting scenario is a nozzle region carrying very large piping moments or complex load combinations where simplified assumptions are not appropriate. If your loads are within the expected scope for the assessment level you intend to use, select yes. If your loads are complex or outside scope, select no. The question 11 asks if external pressure is applicable, is it included appropriately per the selected assessment level and component type limitations. A realistic refinery scenario is a vacuum tower or a vessel that can see vacuum during steam out or certain operating modes. If external pressure is a credible load case, you must account for it. If your case is strictly internal pressure only with no vacuum scenario, you may use NA. If external pressure is credible and you have not addressed it, select no. The question 12 asks if supplemental loads are present. Are they within the scope and limitations of the selected Part 4 assessment level? A realistic refinery scenario is a tall column with wind loads, piping reaction loads at nozzles, and weight effects that create additional stresses. If those loads are significant and govern the case, you may need a higher rigor approach. If you have only typical sustained loads within scope, select yes. If supplemental loads are complex or controlling and outside the scope of simple methods, select no. The question 13 asks if the metal loss is located sufficiently away from major structural discontinuities or otherwise handled with appropriate discontinuity guidance for Level 1 and Level 2 screening. A realistic refinery scenario is thinning close to a head-to-shell junction, a cone transition, or near a reinforcement region where stress fields change rapidly. In those cases, location matters as much as thickness. If the thinning is away from major discontinuities or you have applied the proper discontinuity treatment, select yes. If it is close and you have not addressed it properly, select no. The question 14 asks if you have sufficient thickness readings to establish the minimum measured thickness and the average measured thickness for the affected region. A realistic refinery scenario is a piping circuit where only a few random spot checks were taken at accessible locations, which may not capture the true minimum. Another scenario is a vessel shell, where you performed a UT grid or scan that provides enough coverage to identify the thinnest point and to compute a meaningful average across the region. If you have enough data to support both minimum and average values, select yes. If you do not, select no. The question 15 asks if the measured thickness everywhere is greater than or equal to the minimum required thickness when corrosion allowance and design basis are considered. A realistic refinery scenario is a drum shell where the minimum required thickness is known from design calculations, but your scan finds at least one point below that limit. If any point is below minimum required thickness, select no, because acceptability must be demonstrated by proper assessment or re-rating. If all points meet or exceed minimum required thickness, select yes. Question 16 asks if you selected the correct characterization path, meaning point thickness readings versus thickness profiles, based on variability and damage appearance. A realistic refinery scenario is a straight pipe spool with consistent thickness readings across the area, where point readings may be appropriate. Another scenario is a line with wide scatter, where some readings are much thinner than others, which indicates you need a profile or grid to truly characterize the pattern. If you chose the correct path based on how the data behaves, select yes. Question 17 asks if you are using point thickness readings, have you confirmed the metal loss is uniform wall loss and not localized? A realistic refinery scenario is corrosion that is broadly uniform around a line where point readings reasonably represent the condition. A contrasting scenario is localized thinning under a pipe shoe or a localized patch near a drain connection where point readings can be misleading. If the loss is truly uniform for that region, select yes. If you see signs of localized behavior, select no. The question 18 asks if you are using point thickness readings, do you have sufficient readings with good distribution across the area? A realistic refinery scenario is a crude overhead line where you took 20 readings distributed around the circumference and along the affected length, not just a few points at one location. If your readings are sufficiently numerous and well distributed, select yes. If you only have a handful of readings that cannot represent the region, select no. The question 19 asks if you are using point thickness readings. Does the minimum measured thickness satisfy the averaging protection requirement used in this tool? Meaning the minimum thickness cannot be too far below the average thickness. The purpose of this question is to prevent a false sense of safety from averaging when there is a hidden weak spot. A realistic refinery scenario is a tower shell band where the average looks acceptable, but a few very thin points exist. If the thinnest point is significantly lower than the average, that suggests localized behavior, and you should not rely on point reading averaging. If your minimum thickness is reasonably consistent with the average, select yes. If your minimum thickness is much lower than the average, select no. The question 20 asks if you are using thickness profiles. Have you taken grid or scanned data in the correct plane and density to characterize the metal loss pattern? A realistic refinery scenario is a corrosion band on a vessel shell where you scanned enough area to capture the full thinning pattern and identify the controlling minimum. Another scenario is scanning only a small strip that misses the real minimum. If your grid or scan coverage is sufficient to characterize the pattern, select yes. If it is not, select no. The question 21 asks if metal loss is near a major structural discontinuity, have you taken the added inspection coverage required in the discontinuity influence zone? A realistic refinery scenario is thinning near a nozzle reinforcement area on a drum. You cannot treat it like a simple straight shell region without increasing coverage in the influence zone. If you added the appropriate inspection density where the discontinuity effects matter, select yes. If you did not, select no. The question 22 asks whether you checked for and resolved data discrepancies that require additional readings, such as when a new reading is thicker than a previous reading at the same location. A realistic refinery scenario is an insulated line where CML locations drift over time because access is difficult or surface condition changes affect UT. If your inspection data has discrepancies, you must remeasure and confirm repeatability before trending corrosion rate or making decisions. If you resolve discrepancies and confirm the data quality, select yes. If you have unresolved discrepancies, select no. The question 23 asks whether thickness readings were obtained using appropriate NDE methods and with suitable surface and access considerations. A realistic refinery scenario is heavy scale, rough surface, coatings, or insulation-related access limitations that can compromise UT reliability. If technique selection and surface preparation were appropriate to produce reliable data for characterization, select yes. If the data quality is questionable due to technique or access problems, select no. The question 24 asks whether UT measurements were taken after appropriate calibration and controls, including sound velocity assumptions, temperature effects, coplant, and probe selection appropriate for geometry. A realistic refinery scenario is small diameter piping where probe selection affects the ability to detect thin spots, or elevated temperature inspection where velocity and coupling must be controlled. If calibration and controls were properly handled, select yes. If not, select no. The question 25 asks if brittle fracture or crack-like damage could be a concern. Have you completed supplemental inspection to confirm no crack-like flaws accompany the thinning as applicable for your service? A realistic refinery scenario is a cold service circuit where thinning is near weld seams and brittle fracture is a credible concern, or a service where cracking mechanisms could exist. In those situations, you should not assume thinning is the only issue. If you have performed appropriate supplemental crack detection inspection where it matters, select yes. If you have not, select no. The question 26 asks if any measured thickness readings are extremely thin. Have you applied the required validation precautions before using the values for decisions? A realistic refinery scenario is a severely thinned elbow where 1 or 2 readings are extremely low. Those readings must be re-verified, repeated, and validated because decisions based on extremely thin values require high confidence in measurement accuracy. If you validated the thinnest readings properly, select yes. If you did not, select no. The question 27 asks whether your conditions and data support a level 1 or level 2 assessment rather than requiring level 3 due to limitations or applicability. A realistic refinery scenario is smooth general thinning away from discontinuities with good data coverage, recognized design basis, and loads within scope. That supports level 1 or level 2. A contrasting scenario is complex geometry, strong discontinuity influence, cyclic service, notch-like grooves, or complex load combinations. Those conditions push you toward level 3. If your case fits level 1 or level 2 scope, select yes. If limitations indicate higher rigor is needed, select no. The question 28 asks if remaining life is required. Do you have corrosion rate and the thickness quantities needed to apply the appropriate remaining life method? A realistic refinery scenario is when you must justify the next inspection interval for a circuit with active corrosion. You need corrosion rate trending and the thickness values used in the method so the remaining life estimate is defensible. If you have the corrosion rate basis and the thickness quantities needed, select yes. If you do not, select no. The question 29 asks whether you captured the required documentation, including inspection summary and thickness data organization, and whether you have an in-service monitoring plan suitable for general metal loss. A realistic refinery scenario is a circuit program where you have consistent CML identification, sketches, datasets stored in a repeatable format, and a plan for remeasurement and trending. If your documentation and monitoring plan are in place and defensible, select yes. If your data and documentation are not organized for repeatable monitoring, select no. Now let's talk about what the final result means. If the tool indicates that an API 579 Part 4 fitness for service evaluation is needed, that means your answers suggest there are credible triggers, missing inputs, inspection gaps, applicability limitations, or conditions that require a defendable engineering basis rather than assumptions. That is where you gather the right data, confirm the correct damage classification, confirm the correct characterization method, verify minimum required thickness, and then proceed with the appropriate Part 4 assessment level or escalate to level 3 when necessary. If the tool indicates that a Part 4 assessment is not required, that does not mean the equipment is safe forever. It means your specific condition is within the allowance gate or you did not trigger screening concerns based on your current information. If operating conditions change, corrosion rates increase, a new damage mechanism becomes credible, a new thin point is found, or inspection results change, you should rerun the screening. Let me close with the most important takeaway. This tool helps you avoid the dangerous habit of guessing in corrosion and erosion cases. It forces you to confirm that the condition is truly general metal loss, that the allowance gate is properly understood, that your thickness data is sufficient and credible, and that you are not hiding a local weak spot behind average thickness. Used correctly, it becomes a practical, repeatable gate that tells you when it is time to do the deeper engineering work before you continue operating or re-rate the equipment.